Hello everybody. In this video, we're going to learn about symmetric matrices. And honestly, this is one of my favorite topics because this is going to bring together literally everything we've done in all of the recent videos. So let's just get right into it. Given an m by n matrix A, we define something called the transpose of that matrix. We write it as a to the capital T, and this is not a power, so T is not a number. Here, T is a letter indicating transpose. The transpose of a matrix is an n by m matrix, which you obtain by switching the rows and the columns. And some examples will hopefully make this more clear. So for instance, if M is the 2 by 2 matrix, 1, 2, 3, 4, then M transpose will also be a 2 by 2 matrix, but that first row, 1, 2, becomes the column 1, 2. The second row, 3, 4, becomes the second column 3, 4. Let's say we have a matrix B, which is a 2 by 3 matrix. The transpose of B will be a 3 by 2 matrix. That first row, 1, 2, 3, becomes the first column, 1, 2, 3. The second row, 4, 5, 6, becomes the second column, 4, 5, 6. It's kind of like turning a matrix and kind of like flipping it on its side. Finally, you can also consider the transpose of a vector. You can think of a vector as a something by one matrix. So for instance, here I have the vector 7, 8, which I can think of as a 2 by 1 matrix. The transpose of that vector, think of as a 1 by 2 matrix, 7, 8, but going horizontally instead of vertically. Right, the reason we talk about transposes is because we want to talk about this idea of a symmetric matrix. If A transpose is equal to the original matrix A, then we call A symmetric. So for example, let's say we have the matrix A, which is 5, 3, 3, 7. A transpose, right, this row 5, 3 becomes this column 5, 3, and this row 3, 7 becomes this column 3, 7, but the matrix looks exactly the same, 5, 3, 3, 7, 5, 3, 3, 7. Right? So in this case, A is equal to A transpose, and so we say that A is symmetric. And another way you can kind of think about this, imagine that there was a mirror along the diagonal from 5 to 7. Right? That's kind of the line of symmetry of this matrix. Right? This 3 would reflect across the mirror to this 3. So that's a symmetric matrix. And symmetric matrices, well, they have lots of interesting properties. But to understand their properties, we need to understand some things about transposes. So, a couple of observations. First, if you take the transpose of a transpose, you end up with the original matrix. Because A transpose swaps the rows for the columns, and the transpose, again, swaps rows for the columns, but that turns the columns back into the rows. Take a look at any of the examples on that first page and calculate the transpose again. You'll end up with the original matrix. This is actually kind of similar to inverses. If you calculate the inverse of an inverse matrix, you actually end up with the original matrix. Two inverses cancel each other out, kind of like two transposes do. The identity matrix is an example of a symmetric matrix. Right? I transpose is equal to I. Right? The matrix 1, 0, 0, 1 is a symmetric matrix. And another kind of interesting observation, if you have two vectors, let's say you have the vector v, components v1, v2, and vector w with components w1, w2, if you think about these as matrices, you can't really take v1, v2 and multiply by w1, w2. Right? Because the way we discussed matrix multiplication, these inner dimensions have to match. Right? So when you divide the first into rows and the second into columns, dot products would make sense. Right? So because of the dimensions of these matrices, this matrix product is undefined. You can't calculate that. However, if you take the first vector and transpose it, right, so the 2 by 1 becomes a 1 by 2, then you can calculate this as a matrix product. Right? V transpose times W, you have one row times one column. And so calculating that, in the same way we calculate the product of matrices, gives you a 1 by 1 matrix. The calculation consists of a single dot product. Now, a 1 by 1 matrix is really just a number with brackets around it, so we often drop the brackets. But yeah, V transpose times W is really just the dot product of V and W. And so transposes kind of naturally lead us back to dot products. Here's another interesting observation about transposes, and every single one of these observations, we're not just talking about them for fun, even though it is fun, they'll all become useful in the discussion that's going to follow. So here's another observation. Let's say you're calculating a matrix vector product. So you have the matrix A times the vector V. Let's write V as x, y. And the matrix A, let's write that as A, B, C, D. When you calculate that out, you get AX plus BY and CX plus DY. Now, if you have to calculate the transpose of that product, and calculating the transpose of that vector, you get a horizontal vector, right? A 1 by 2, AX plus BY, then CX plus DY. Now, interestingly enough, let's say you want to calculate V transpose times A transpose. Right? V transpose you can think of as a 1 by 2 matrix, 1 row, 2 columns, and A transpose is still a 2 by 2. So this product, this matrix product, is defined, but when you multiply that out, you get exactly the same thing as A times V transpose. So in other words, the transpose of the quantity A times V is equal to V transpose times A transpose. Or, just if you want to think of this as a catchy phrase, the transpose of a product is a product of the transposes in the opposite order. And so something to keep in mind. Now, here's something really fun, and we're going to bring this back to eigenvalues and eigenvectors. We've talked a lot about calculating the eigenvalues and eigenvectors of a matrix. We've seen that's useful for diagonalization, for population modeling, for all sorts of things. But if you try to calculate the eigenvalues and eigenvectors of a symmetric matrix, this isn't always true, but if your matrix is symmetric, it turns out that those eigenvectors, their dot product is 0. And that's provided that the eigenvalues are different, but the eigenvalues are basically always going to be different. Yeah, symmetric matrices have perpendicular eigenvectors. And what I mean by this is the angle between those two vectors. And if the dot product is 0, a long time ago, we talked about a dot product formula that let us calculate the cosine of an angle between two vectors. And we learned that if the dot product of two vectors is 0, that means the cosine of the angle between them is 0. But that only happens when the angle is 90 degrees, when that's a right angle. So V and W are perpendicular, which we also denote with this symbol, which looks like perpendicular lines. Now, why is this true? Why do symmetric matrices have perpendicular eigenvectors? Now we get to use all of those observations. Right, so let's say we just happen to multiply the dot product times this eigenvalue lambda. Well, I can pull that eigenvalue through and attach it or multiply it by one of these by one of the eigenvectors, right? So lambda times the quantity v dot w is also equal to lambda times v dot w. Now lambda times v, we know that this is an eigenvalue-eigenvector pair. So lambda times v is the same thing as a times v. So I can replace lambda times v with a times v. So I have a times v dot w. Now it's time to make an observation. A dot product can be rewritten using a transpose and a normal matrix product. So I can rewrite the first dot with a second, can rewrite that as the transpose of the first times, meaning matrix multiplication, times the second. And so I can replace this dot product with this expression. Time to use another observation. I have a transpose of a product. I can rewrite that as the product of the transposes in the opposite order. So here, I have V transpose times A transpose times W, and these all being matrix multiplications. Now, A is a symmetric matrix. I haven't used that fact yet, but we're going to use it now. That means A transpose is equal to A. So I can replace A transpose with A. And now I'm going to use associativity, and I'm going to group this multiplication. I'm going to do the second multiplication first. And so now I have V transpose times A times W. Now remember, if I have the first transpose times the second, that's equivalent to a dot product. Right? I'm using one of those observations in reverse now. Right? First transpose times second can be written as the first dot with the second. All right. And A times W, right? Well, this is again an eigenvector, and I know that A times W is equal to the scalar multiplication kappa times W. So I could replace this with that. Right? It's like I'm reversing the observations in this direction. Okay, so A times W replaced with kappa times W. I have V times kappa times W, V dot kappa times W. And I can take multiplication of kappa and I can pull that outside the dot product. So I have kappa times the dot product. I started with lambda times the dot product, got all these equalities here, ended up with kappa times the dot product. So lambda times the dot product is kappa times the dot product. Let's take the one on the right, subtract it from both sides, so moving it over to the left. So I'll have lambda times the dot product minus kappa times the dot product. I'll factor out that dot product. So I have lambda minus kappa times this dot product is equal to 0, because there's nothing left on the right-hand side if I move this from the right to the left. But if the product of two things is equal to 0, that means one of those things needs to be equal to 0. And well, remember we said that lambda and kappa are different. Since lambda is not equal to kappa, lambda minus kappa is not equal to 0. This first term is not equal to 0. That implies that the dot product, I forgot to write the punchline, the dot product must be equal to 0. There should be a little equal 0 here. So yeah, the takeaway from all this, you don't have to rederive this on an exam or anything, but the takeaway is this following sentence, is that the eigenvectors of a symmetric matrix are perpendicular. It's kind of interesting. So a matrix being symmetric is kind of nice, and that lends itself to other nice properties. But wait, it doesn't stop here. So now I really want to go back a fair number of videos. A long time ago, we talked about things called linear functions. And a linear function is basically a function with vector inputs and vector outputs, and it behaves nicely with respect to the vector operations. right? You can kind of simplify it or distribute it through vector addition and scalar multiplication. So if f is a linear function, then f of v plus w is equal to f of v plus f of w. Also, f of c times v is equal to c times f of v. That's not true for all vector functions, but if these are both true, then that function is called linear. One of the great things that we learned about linear functions is all linear functions look like matrix multiplication. And to figure out that matrix, all you need to know is f of I and f of j, where I and j are the standard basis vectors in two-dimensional space. So I is the vector 1, 0, and j is the vector 0, 1. And so if you know those two outputs of the function, if you know those two values, that actually tells you what the columns of the corresponding matrix are. And that was an entire lesson by itself. Another thing that we learned, we spent some time talking about rotation matrices. And rotation is a linear function as well. You can write rotation using matrix multiplication. And by rotation, I mean we're rotating the points around the origin, right, in the plane. If you want to rotate counterclockwise around the origin by an angle theta, we figured out that this is the matrix you would have to multiply points by. And so you would figure out, starting with a point, multiply it by this matrix, and the result is the new location of the point. Okay, so that was a trip down memory lane. So try to remember those two facts because they're going to become important really soon. Let's assume that we have some kind of a linear function, right? Any linear function. And let's say that f of the vector I, let's call that vector v, so let's say that's v1, v2. That's the first column of our matrix. And f of j, let's just call that vector w. That forms the second column of the matrix. And so this is always true for all linear functions. We know we can write the matrices. However, if you know a little bit more about these outputs, right, this vector v and this vector w, if it so happens to be true that the length of v is 1, and if the length of w is 1, and if their dot product is 0, granted, that's a lot of ifs. But if all three of those conditions are true, then this matrix has to be a rotation matrix. Okay. Let's learn why that has to be true. Right, so this is basically the picture that explains it. Right, so you start off with a standard basis vector I, that's 1, 0, and the basis vector j, that's 0, 1. And this purple circle here, that's the unit circle. So it's a circle of radius 1. Right, so I, right, the endpoint of this vector is on the circle, and the endpoint of j is also on this circle. And let's say that f of I is v, and f of j is w. Now, where did those vectors lie in this diagram? Right, well, if v and w have length 1, that means the endpoint of v and the endpoint of w also must lie on this circle. Right, so wherever they are, right, their endpoints are also going to be aligned with this circle. Now, in general, maybe v points here, maybe w points down here, or w points over here, maybe v's here and w's over there, who knows? But if you also know that v dot w is equal to 0, that tells you that v and w are perpendicular. So once you know where v is, that kind of forces the position on w, right? Because this angle between v and w must be 90 degrees, much like the angle between the vector I and the vector j. So, right, what can we say here? I'd like to label these three angles to make this a little bit easier. Let's say the angle between I and v is alpha. The angle between V and J is theta. The angle between J and W is beta. Right? I know that I and J are at right angles to each other. Right? Since I is perpendicular to J, that means alpha plus theta must be 90 degrees. Similarly, because V and W are perpendicular to each other, right, this angle is 90 degrees, so theta plus beta must also equal 90 degrees, since they're perpendicular. Hey, that means alpha plus theta is equal to beta plus theta, which means alpha and beta must be the same angle. Right? So alpha is actually equal to beta. Right? I rotates into the position V, right? It doesn't change the length, and it rotates by this angle, but the same thing happens to J, right? J is rotated by the same angle, right? The vectors aren't stretched or shrunk. The only change, this transformation, is rotation by this angle theta. Right? So if these conditions happen to be true, this has to be your rotation matrix. Right? In this case, it would be cosine alpha, negative sine alpha, cosine alpha. And that's why this set of conditions forces the function to correspond to rotation. Now let's bring all these different points together. Let's start off. Let's assume that A is a symmetric matrix. Symmetric matrices rock. Then we're going to diagonalize that matrix. We know how to do that. We write it in the form P times D times P inverse. P is the matrix of eigenvectors as columns, and D is the matrix of eigenvalues along the diagonal. Now, remember, when we calculate the eigenvectors, there's lots of answers. There's lots of ways you could choose an eigenvector, right? Because there's free variables. And in fact, here's something which is useful. Right? Let's say that lambda is an eigenvalue and v is an eigenvector. So we know A times V equals lambda times V. I could take this equation and I could multiply both sides by C, some constant. And then I could kind of pull that factor of C through, and I notice that A times C times V is equal to lambda times C times V. But that means the matrix multiplication is the same as scalar multiplication, which means C times V is also an eigenvector. In other words, any scalar multiple of an eigenvector is another eigenvector. So, because A is symmetric, one of the things we discussed earlier is the eigenvectors of a symmetric matrix are perpendicular. That means their dot product is 0. Right? So this is automatically true. Right? If these two things are perpendicular, it doesn't matter if you rescale these vectors, which is important because no matter what I pick for my eigenvectors, I actually want to replace them with a scalar multiple so that the lengths of the eigenvectors are equal to 1. Right? I want to pick the eigenvectors for each eigenvalue that have length 1. Why do we want to do that? Well, then these three conditions force this matrix P in the diagonalization. This matrix P is going to be a rotation matrix. Right? So if you have a symmetric matrix in the diagonalization, this matrix P is actually this. This is the key idea. For special matrices, for symmetric matrices, the diagonalization is also special. The diagonalization is all about rotations. So let's do an example to really make this clear. So here's a matrix A, and this is a diagonal matrix. Oh, no, sorry, this is a symmetric matrix. We want to diagonalize it. So the matrix A is 3, 2, 2, 3. I'd like to diagonalize it, but specifically, I want to choose the matrix P to be a rotation matrix. So we see how that works. So we're going to diagonalize. It's going to be exactly the same process as before, plus one extra step. When I pick eigenvectors, I'm going to convert them to unit vectors. And that's going to turn this into a rotation, which is kind of cool. So, well, to calculate the diagonalization, you know the drill. We calculate the determinant of A minus lambda times the identity matrix. So subtract lambda from these entries to calculate the characteristic polynomial, calculate the determinant, this expression, expand, we group like terms, then we factor. The eigenvalues are 1 and 5. The diagonal matrix is 1, 0, 0, 5. For the first eigenvalue, lambda equals 1, subtract that from these entries, convert to the system of equations. In this case, they're legit the same equation. So you can pick whatever you want for V1 and V2. Pick some easy numbers. I picked V1 equals 1, V2 equals negative 1. It satisfies these equations. This is an eigenvector. Now this is the part where it gets a little bit different. This is an eigenvector, but we want to pick an eigenvector that has length 1. So we're going to take this eigenvector and we're going to multiply it by a constant. The result is still an eigenvector, but it'll have length 1. The way we calculate a unit vector from this vector, first we have to find the length of this vector. Remember that, the Pythagorean theorem? It's the square root of the first part squared plus the second part squared. So the length of this vector is radical 2. To turn it into a unit vector, we're going to multiply it by 1 over its length. So we're going to replace this eigenvector with this eigenvector, 1 over rad 2, negative 1 over rad 2. Right? It's not as nice as present. It might seem like it might be nice to work with whole numbers, but being able to interpret this as a rotation really helps us understand what's going on a lot better. Similarly, same process for the second eigenvalue, kappa equals 5. Right, go ahead and set up your equation, subtracting the eigenvalue from the diagonal entries. You get your system, pick an eigenvector, and do the same thing. Now it's just a coincidence in this problem that the length of this vector is again radical 2. They don't always have the same length, but in this case they do. So we use the length of this eigenvector to scale this eigenvector to get a new eigenvector. Right? So again, this will be our choice for W. So now for the diagonalization of this matrix, as always, it's P times D times P inverse, but we're using these scaled eigenvectors, these unit eigenvectors, as the columns of P. Same diagonal matrix, and P inverse, we'll calculate that a bit later when we need to. The cool thing is, this is a rotation matrix. Right? Because we made these unit vectors, guaranteed we can also write this matrix in this form. How do you figure out the angle theta? Well, just match up the terms. 1 over radical 2 equals cosine theta. Right, so 1 over radical 2, you could also write that as rad 2 over 2. And this is one of those nice angles. It could be 45 degrees. However, it could also be negative 45 degrees. Right? There's two values of the cosine function which give us this as a result. So it's going to be plus or minus something. To determine which of these two signs is correct, we take a look at sine. In this case, sine is negative, so we're going to go with a negative sign here. Right? Trigonometry tells us that theta must be negative 45, right, for sine theta to be negative 1 over radical 2. Right? If you were to graph the sine function, right, the positive angles from 0 to 180, right, those all have signs that are positive. The negative values of theta will give you negative outputs for the sine function. Right, so this rotation matrix, right, this is rotating by negative 45 degrees. Now, what about P inverse? Right, how do you calculate, Lights went out again. That's how I know the video is getting long. Go ahead and turn those on. All right. So we need to find the inverse of that matrix. And we know what the inverse formula looks like. Right? The inverse of a matrix, we have to calculate the determinant. And the inverse is 1 divided by the determinant. Then we have to swap these two entries on this diagonal and then negate these two. But for a rotation matrix, calculating the inverse actually leads to some nice simplifications. The determinant of this matrix is cosine times cosine minus sine times negative sine. So in other words, the denominator is cosine squared theta plus sine squared theta. And remembering your trig identities or the Pythagorean theorem, this is equal to 1. Right, so this whole matrix is just getting multiplied by 1. Furthermore, switching cosine theta with cosine theta, no real change. Negating these two, and again, they both have sine theta. It's just like the negative sign jumps from here to here. In fact, the inverse of a rotation matrix looks a lot like the original rotation matrix, except that negative sign, the negative in front of the sign, jumps down to the negative in front of the other sign. In fact, P inverse is P transpose for a rotation matrix. And the takeaway sentence here is for a rotation matrix, inverses and transposes work out to be the same thing. And there's actually a few ways to see that this is true. Another way to understand this is, well, if P is rotation by theta, P inverse should undo whatever P does. P inverse should be a geometric opposite. In this case, if P is rotation by theta, P inverse should be rotation by negative theta. So to calculate P inverse, we just put a negative theta in for theta in each case. But because of the symmetry of the cosine function, cosine of negative theta is the same thing as cosine of theta. And because of the symmetries of the odd functions, like sine theta, right? Sine of negative theta is negative sine theta. The negative just comes outside. Negative sine of negative theta is negative negative theta, or negative negative sine theta. Those two negatives cancel out. At the end of the day, just either one of these explanations, whichever one makes the most sense to you, they both lead you to the same observation. For rotation matrices, inverses are transposes. Right, so to calculate that P inverse, it's very simple if you happen to be working with a rotation matrix. Right, and that's the trade-off. It's a little bit more work to take your eigenvectors and scale them to have length 1. However, it makes calculating this inverse extremely easy. Now, let's do an exercise. Right, and this isn't going to be a full calculation. You've had plenty of practice calculating diagonalizations. And we're going to do some more of those in the next video anyway. Instead, I'd like you to think about what we've done in this video. In particular, I'd like you to think about a matrix which has this form. Right? A matrix which we've diagonalized. Usually a diagonalization looks like A equals P times D times P inverse. But in this case, when A is a symmetric matrix, inverses of a rotation matrix are transposes. So the diagonalization looks like P times D times P transpose. But in this case, let's assume we start with this piece of knowledge. Right? Let's say that we happen to have a matrix. We don't know if it's symmetric, but let's assume we know A is equal to P times D times P transpose. If we start with this piece of information, it turns out any matrix which can be written in this way must be a symmetric matrix. In other words, it's biconditional. Right? So in other words, starting with the fact that A equals P times D times P transpose, show that the transpose of this, show that A transpose, which is the transpose of the quantity, P times D times P transpose, show that that is equal to the original matrix A. And therefore, A must be a symmetric matrix. Right? In this case, you're really going to draw upon the observations from before. Right? We're not doing this for any specific matrix. Right? We're not carrying this through for a numeric example. But remember those observations, like the transpose of a product is the product of the transposes, but in the opposite order. Remember, the transpose of a transpose gives you the original matrix. The transpose of a diagonal matrix, right? It's going to be the same thing. You can check if you switch the rows and columns of this, you'll end up with D again. Right? Show how you can take those observations and show that this expression is equal to this, which is equal to A. And so we're thinking deeply about a lot of big concepts here. And so that's going to be it for this video. Symmetric matrices, in particular, have a very nice diagonalization. And we'll see why this is useful by doing another application of diagonalization related to something you might have learned in a high school algebra class called conic sections. But we'll talk about that in the next video. That's definitely it for this video. Thanks for watching.